with that, I'll get started, and hopefully we can do him and his company justice and these meetups. Okay. So my arrows aren't working. Okay. So we at Zebrium we sort of had this idea about what's the problem we're out to solve, and what are people finding and experiencing in today's kind of DevOps SRE world. So there's we looked at the problem with this in mind, and basically the bottom line was humans really don't scale with complexity. So what do we mean by that? So if you take a problem scenario, any problem scenario, you're always going to be faced with understanding or seeing symptoms happen, and then trying to get to the root cause of that problem. And so in that world, when you're, maybe you're monitoring something or what have you, when you know the cause and you know the symptoms, DevOps teams can, approach near total automation for those things. They know when they see this event that it means this, and they might even have runbook automation in place. So it's, you can really do a lot when you know what you're looking for and how to resolve it, what the root cause is. But if you only know cause or symptom, it gets a lot tougher. I mean, especially if it's just a symptom, you can sort of be alerted maybe through Prometheus or some such thing where you see latency spiking. So there's a problem. You don't know what there is there underneath it that's causing it. And you're almost assuredly, in most cases, going to start digging through logs to get to that root cause. So even in that second case, you might have partial automation, but you're still doing a lot of manual effort to sort of understand the root cause of the problem and get that solved. But then there's a whole another class where it's both unknown cause and unknown symptom. So you don't even know these things are coming. You have no way to detect them. They just happen. And then that's entirely manual. And it's usually manual search. You're probably searching through logs. And you're probably searching through millions and millions or billions of logs that you get that day from very complex systems. And so if you look at sort of, the history of these things back a decade ago. So what happens when there's an incident? You've got more probably a monolithic system. Maybe it's got, maybe there's a server and a database and a front end or something, but it's not very complex. And when there's an incident, it doesn't affect many people. It's maybe running in your own on-prem environment, so it affects your users. The incident complexity is lower because there's just not that much to the app. There's not, thousands of microservices running, for example. And, the human bandwidth, when you want to fix that, you could start working on the problem. Maybe you call the support line, you get somebody, they start to help you through it. But today, it's an entirely different story. When there's an incident, the impact can be enormous. Like imagine something like Stripe, if they go down. So you're going to affect thousands of users. You're going to affect all of their customers. You're going to affect financial transactions and the potential livelihood of the company itself. It's a huge impact in today's environments and very complex systems with thousands or hundreds of microservices, maybe thousands of instances of things, all communicating together with tons of logs being generated, all sorts of metrics that you want to monitor and so on. It's just horribly complex. However, the human bandwidth has not gone up. I know you guys are probably all smarter than I am, and you probably got a lot more of that bandwidth than I do, but you're not 100x more efficient than you were a year ago, or even a decade ago, or anything. So you still have that problem. So humans just can't scale with the complexity of the systems that we're building nowadays. So that's the problem we were trying to address and solve. So how do we do this? What's our solution? Well, if you take a look out there in the world, there's all sorts of tools and things like Elastic or Prometheus itself that are logging metrics, tracking them, allowing you to search when you have a problem. A lot of manularity, a lot of setting up of rules. It's very commonplace nowadays. Everybody's doing it. It's sort of not saving a huge amount of time in getting to root cause. Of course, it's making somewhat more efficient. On top of that, we're seeing a lot more anomaly detection. And generally speaking, it's mostly around metrics, rarely around logs. But there is a lot of forward movement around anomaly detection. All of these vendors typically have it, like Elastic and Sumo and Datadog and so on. And they're trying to spot outliers or changes in patterns in the logs and the metrics, and again, predominantly probably metrics in most cases. And you you get anomalies. So now you've actually maybe narrowed the search a bit. You're not dealing with billions of things you have to look at. You've got an anomaly. It's probably at play. It's probably something that focuses you somewhat down to closer to the problem. But it's not enough. And this is where we come in. So what we're after is solving these the massive amount of anomalies you might get in a way where you actually are boiling and distilling those down further to an incident and to root cause. So our solution and our goal here has been to auto-detect incidents with the root cause embedded in the detail of that incident. So now we're distilling millions or hundreds of millions or billions of lines down to something around the order of tens of events that are important and metrics that may correlate with those anomalies in an anomalous way themselves. And that's our goal and our solution. So let me walk you through what that means and what we do. So how did we get started? So I know this is a Prometheus meetup. It's all about metrics, and that's maybe what you thought you came to hear about, but we didn't start there. We started with logs. Okay? So why did we start with logs? Well, ultimately, two big reasons. Number one, when you want to get to root cause, typically metrics are not going to get you there. They're going to get you pinpointed maybe to a service that had higher latency, maybe on the front end or in a database. So it'll get you sort of in the right space. It'll probably get you to even the right node of something. But it's not going to get you ultimately to what caused that latency. That is typically going to be the logs. So the logs are immensely valuable when it comes to root cause analysis and getting to that root cause of that problem. The second reason we started with logs is really simple. Logs are very hard. So what do we mean by that? Why are dealing with logs so hard? So first of all, formats change. So if you've ever looked at logs or dealt with developers and so on, you've probably all seen this. Formats of those logs can change. So developers, when they're writing the code, they think it'd be a great idea if you had this printf statement now and it gets logged into syslog that tells you what's going on. Maybe it's an error level event or a warning or what have you. They're going to write some text with that. And at some point, they might change it. So you're dealing with, if you're making rules on those events, those changes. So your rules are dependent on what that log event looks like, and it's likely to change over time. So that's the first thing why it's hard. Just understanding that they can change and also that they're very different. So they change across different kinds of log streams, like a Apache error log does not look anything like a syslog in the way it's structured, in the sense of where the timestamps are or the sort of style of the event themselves, where any of this information is located. So they're just all different. Okay? Next thing is the parsing of these. So you can build parsers. You're typically going to do something with regular expressions that are going to define what fields out of that event that you're interested in you want to capture. So you're going to write a regex that captures certain pieces of the data out of that event log. Now, when it changes, you might not be capturing the right thing anymore. In fact, when that happens, if something changes and your regular expression, there's two problems. When something changes with that, you might not capture that anymore correctly because it's changed. So you're going to miss things. And on the other hand, unless when you're building that parse rule, you've got a lot of examples, not only of the one you're interested in, but even of the ones that you're not interested in, so that you're not going to capture those ones by mistake. You don't want all these false positives. It's a very difficult problem because you're probably not going to go look at the thousands and thousands and thousands of different events across all these services to make sure that the one you're picking out and writing the parse rule for is going to get exactly what you need and only that, and will always get exactly that. It's a very difficult problem, very, very hard problem to solve, and this is one of the things that we set out to do. And typically experts are needed to interpret these logs. So when you are doing root cause analysis, you might see, oh, here's this strange looking event in your logs, and you don't know whether it's relevant. But just by looking at it in its own context, in that context that you're in, you don't know if it's important to the problem at hand necessarily. You might very well need to talk to the developer or somebody who's more expert in what really did that mean. Because when we write those syslog events, it's not all just spelt out in plain English always. You'll see something like dy equals 42 and is less than 3. I mean, it's all these things. You don't know what any of that stuff means or where it's relevant to the problem or not. So that's another problem with just depending on the textual context of a log event at that point in time. There's more that you need to understand its relevance to the problem, not just what it says. And then, of course, the real problem, or another big problem, is that the applications we deal with and that we're deploying, they're all bespoke. And what we mean by that is, take, for example, a Nginx or an Apache error log. There's probably 100, I don't even know how many, there's probably hundreds of parsers or people that have written parsers for those log types, where they can really parse out the 400 errors and the 500 errors and do all sorts of nifty stuff with them and turn them into metrics so you can see how things are behaving and everything else. That's all over the place. But your apps are not just that. They're not just these open source things that are common out there and that people have built parsers for potentially. It's all your stuff. The real value of what you're building is your IP, and you're building that yourself, and that's all new stuff. And you're probably putting log events out there, and you can't go get a parser for them. So you're dealing with, again, maybe 1,000 unique event types that you've put in, sprinkled through your app. You got no parsing for them. So given that, you can't instrument for the unknowns because you haven't built parsers for everything. So now you can't figure out that I need to monitor this when this happens and that when this happens, because you just don't know how to look for everything. So that's a big part of why this is so hard. Okay? So how do we solve that? So our real secret sauce is a couple of things. Number one, and first and foremost, and what we started out doing, and this is Larry as the CTO and that I introduced earlier, and he started on this several years back before we were even formed as a company. He was off doing a bunch of this research and trying to build models and so on how can you automatically, with no human intervention, structure logs of any type into a relational structure such that you can then do really interesting things on it because you've got them all structured. So that was, sort of the foundational element of the company. Let's get things structured. And then there's all sorts of things you can do, as I said, with machine learning on top of that to figure out where there's anomalies and so on. So what do we do with that? So imagine for a moment that you were sitting down and you're going to write one of those parsers, okay? So you're going to look at that log line. You're probably going to want to get a few examples of it so you can see the human eye, and because you have some background knowledge of it, it's relatively easy for the human to look at that log and say, this part here is an IP address and it's going to change over time, and this part over here, the fourth word over, is the host name, and this is the whatever, the disk ID or the latency number and so on and so forth. You're going to look at that log event and you're going to pretty much know its content and what you want to parse out because it's variable. So you're going to be very interested in the variant parts of that log event and capturing those. It's not as simple for a computer to do all that, but that's what we did. So what do we do? So we're looking at every log event as they're coming in. So when you deploy us with a Helm chart. So it's quick and easy, command. You now are collecting data, through our log collectors and sending it back to our engine. And at that moment in time, we're starting to learn what those events look like and how to structure them. So as we're seeing data coming in, we're looking, and if we take a look at one log line, we're going to have the same problem. It may be the human. Like if you don't really know it really well, you don't know what parts change. If you only look at one thing, you don't know what the variable parts of that log event are. But it's the case that we've found that most of the log events are seen, very frequently and often enough that it doesn't take a lot of time to see more than one of them. Okay, that's generally our findings. So as we're ingesting that set of logs, we are looking and we're saying, okay, we've broken this thing down, we've tokenized it, we've broken it all out, and we found some integers or other words and blah blah blah. We've broken it all down, and we're able to see when the next one comes in. We're looking and we're sort of doing some analysis on it to see whether it looks very similar to something else we've seen using these machine learning techniques. Now, if we find something that, oh my God, it looks very similar in a lot of regard, However, this thing seems to be changing. We now know that that's probably a variable. If it's an integer or a number, float, then we actually assume it's a variable because they typically are. But if it's just a string like the word stopped, you don't know that that's going to be a variable until you see the word started. Okay, but when you do, you now know at that position, that part of the event, it's the same everywhere else, but that part can change from the word stopped to started. Okay. The other thing that are part of every event are all of the prefix stuff. Like again, these Nginx logs or whatever, the sort of the first, 10 fields in there are going to be things like the timestamp and the time zone and the severity and so on and so forth. And if you looked at that log, they would all look pretty much the same. And then to the right of that is going to be the text of the event. So what we're doing is we learn the prefix. So when we're looking at a log stream, we can see, it's all the way over to word 8 or whatever, token there. It always looks the same. So that's going to be the prefix. And the stuff to the right of that is different most of the time. So that's going to be the actual event message. So we can figure that out. So now we're going to construct a table. So we're going to turn that log event that we see. Let's say we saw 2 of them. So we've got a difference between them. We're going to turn it into a table. So we're going to create a SQL table, fully compliant SQL, where the name of that table is going to be essentially the static portion of that log event, the part that didn't change. We're going to name the table that. So when you look at it, if you want to look at the table, it'll actually sound familiar. It'll actually look a lot like what the log event did. You probably recognize it if you've ever seen it before. And the variable parts will be columns in the table. So there will be a column in there that's probably called something like, I don't know, whatever we find word near it that sort of may represent that start and stop. So I'll call it state. Like a message said state stop, state started. So we call the column state. And then we have prefix columns that are called timestamp and severity and so on. So at the end of that, we're going to have a complete structured set of events. Now, what happens though if we don't see one, a second one? We see one of them only. We won't know what the variable parts are. So we're probably going to get it wrong. We're going to try to err on the side of structuring more if we can. And then by that, I mean, if we see things that look like IP addresses, we'll put them in columns and we'll type them as IP addresses. We see ints, we're going to put them in columns. We'll type them as ints and so on. But we may not get the other stuff correct because we haven't seen any variations. So what happens next is when we actually see another event come in, and it could be, 5 minutes later, it could be a day later. When we're parsing that and doing the same machine learning on it and tokenizing it all and everything else, we're figuring out what it looks like. If we see that it looks like this other one that has not yet been structured, but we can see in this one that we are seeing a difference in, let's say, that start and stop position, we actually will build a new table for that one, and it will have that structure. And the word stop, let's say, we'll get into that column, and it'll be the only row in that table at that point. But we will know to merge those two further down in the pipeline. So a few minutes later, the merge process will kick in, and it will know that those two tables are actually supposed to be one, and it's the one that got the latest structure, and it will move the data of the other one into that structure. So now we've just learned, because we've seen more, doesn't matter when we saw it, we'll do the same thing as if we'd seen them very close together when we were initially structuring. So now we've got all of these things beautifully structured, and we didn't need to understand any known prefix formats. You don't have to understand any specific log type keywords like, oh, this looks like an HTTP log or an access log, so we'll figure out what we do with that one. We don't need to know the event grammar. We don't have to have anybody tell us that, what the syntax of these things look like or anything else. It's just 3 text logs, and now they get structured. So I'll break there and just see if there's any questions, or if everybody's sort of following that, or if I sort of went too fast or missed something that wasn't clear. Okay.
I'm good. I'm just eager to see the demo.
Same here.
Well, we will get to a demo.
All right, very good.
And guys, we've got Larry on, and Larry, jump in whenever, like when I'm off the rails here or whatever, just like get me back on or interject when you've got some more detail that's interesting. Please jump in. So so what that means, and this is a fairly quick, simple example here, but this is what we mean by prefix and then that contents to the right. So the prefix, again, it's the same log stream. So as we're ingesting, we're doing this machine learning at a log stream level. We're not trying to learn across structure across different streams. Like we're not going to try and learn structure from the logs that are coming from the database with the logs that are coming from, the web server. But then it makes no sense. So, and part of that is that we're going to sort of start learning the prefix. The syslog is a bit interesting because there's, syslog tends to house logs or events, I guess, for many different processes, and they're not consistent in the way they write their prefix information. So even a syslog log stream, we might recognize or understand and do the right thing with, 5 or 6 or 7 different prefix formats. So we sort of weave through that to understand which lines sort of are grouping into a particular prefix versus some other prefix format. But that's just, sort of the case with everything. We figure out that prefix, and then to the right of that, we've got the content. So the actual event message that the developer wrote in there. And this is a fairly simple example just to illustrate a couple of real quick points. So this is the sort of the variant parts are, sort of embedded in here where you can see numbers here and you can see, keyword errors, and there's a number of errors. So the bottom line is we take that and with absolutely no human intervention whatsoever or pre-training or anything, we would have created a table that we would call this. So you can see that it's made up of the static portions of the event. So these fields here that never changed, they're static. The word weight is static, the word MS is static, so is word errors. So we create a thing that's called stat SD weight MS errors. So if you look at that, you probably have a good notion of what this is about, potentially. And so we try to do that and make it, something that would become familiar to you just by looking at the table name if you were to go in and do that for some reason. And then we've created all these columns. So you can see that we've created columns and we've sort of typed them correctly. So this is typed as a time stamp with the time zone information. We've typed severity as a string and so on and so forth. And you can see down here where we have the column name here, we call it weight MS. So there's static portions that were around that number. And then that's a type int, and then you see those, I guess, latencies or what have you. And then similarly for errors, we called it errors as a column name, and it's a type int, and then you see the data in there. Okay, so that's just an example of, we chose a simple one here just for the sort of clarity of how you can see it map easily to these columns and the parts that are changing versus static. So that's what we do. All right, so now we've done all this structuring. That was a big thing. I mean, that was what Larry had spent a lot of time, again, before the formation of the company, just to get that stuff working. And I tell you, we've ingested logs from hundreds of stacks, and it just works beautifully. I mean, there's really nowadays nothing that stumps us. I mean, it gets in there, and it works really well. And so I'm talking about structure. Now, what needs to work on top of that, and the reason we did the structuring in the first place, is because we want to do incident and root cause detection. And so how do we do that? What does that mean? Well, once you have sort of this whole catalog of events, we call them event types, E-types. So now you have a whole catalog of these things. And by that, I mean, like let's say you get 1 billion logs a day. They're not 1 billion unique things. That's going to distill down to maybe 1,000 or 2,000 unique types of events that, printf statements in the code. And so now you got 1,000 or 2,000 of these things that will equate to 1,000 or 2,000 tables. So what do we do? So on each of those event types, and you can see, we use that terminology here. So we have event type 1 and 2. So we start learning patterns of those. So what do we mean by patterns? So for example, we will start learning the frequency of that event. Like it's happening 100 times. When it happens, it sort of comes in a clump of 100 times per minute. And that happens on a periodicity of every hour. So we track that. So we now know that. So we're learning what these things tend to look like and how they behave at an individual E-type level. So we're learning all of that for all of them. Now, what happens when they break pattern? So things that might mean something has broken pattern would be, in the case of this example here, you can see that in this event type 1, it wasn't occurring at all, and now it has occurred. So that would be classified as a rare event. And that's anomalous in nature, because we don't tend to see that thing. Now we did. So we would mark that as an anomaly. Okay? This event type 2 is one of these ones where it's got this beautiful periodicity, and maybe it's happening 10 times in that little time there and 10 times there. And, these are spaced an hour apart, and all of a sudden it goes wacko right here. So that's a change in the pattern. So that would sort of lead us to believe that's an anomalous thing going on right there. So we're going to generate an anomaly for that E-type. So that's going to happen then. Okay, so now we got that reason for an anomaly being created. This is another one where it's happening on a very periodic basis, and then all of a sudden it stops. Maybe it's a heartbeat. Maybe it's a heartbeat that's going between clusters in a database, and all of a sudden it stops. You want to know about that. That can be disastrous. Okay, so that's the sort of thing that you can figure out once you have typed every event, and you can learn from how they appear. The next thing is this, where it's not really occurring at all, and now it's started. So something bad happened, and we all know this, systems coming along, something bad happens, all of a sudden you get a spewing amount of log events. Okay? So you want to know that this is a new thing happening. It looks very similar to this pattern. They're very periodic, but they just started. There's something probably happened here. So that's an anomaly. Okay? But it's not enough to just know that things are anomalies. Like let's just, for an example, say that your anomalies catch the 1 in a million thing. 1 in a million. That's great. Sounds great. But it's not so great if you get 1 billion log events a day. That means there's 1,000 of them. What are you going to do with 1,000 anomalies? Are you really that better off? I mean, you might be, but you might not be. There might be a lot of false positives in there, but you're going to need to look at 1,000 things. It's not going to make your SREs and your DevOps team very happy if that's what they're dealing with. It's gotten better. They're not looking at 1 billion things, but it's not great. So what makes it great? So if you take a look, so that all those blues, pretend that's your 1,000 anomalies. Okay. What we then do is we take a look at those anomalies to see if they're clustering together in time in a manner that is something out of the ordinary. So statistically, they shouldn't be happening together. We don't see them happening in that, and they're happening across different systems or log streams. So now you have a set of those anomalies, like out of, if you got 4 anomalies and nothing else was happening across different log streams, you probably don't care about them. But if you have a set of them that's based on what we see in history are statistically unlikely to all be occurring together in the same short window, there probably is something going on. And that's going to distill down to a lot less than 1,000. You're going to get that down to, what we typically see is something in the tens of events, anomalous events that have clustered together in that manner, in the way we do this, that we then pull together and create an incident from. So this is what an incident looks like in our view, and we'll show you the demo here soon, but that red thing there, that's what we call a hallmark event. And so we create this incident automatically, and that hallmark event is out of all of those anomalous events that make it up, and again, there might be 10 or 15 of them, 40 of them or something like that, but there's not thousands and there's not hundreds, there's something in that order, tens. But that one is what we feel, for various reasons, and have determined as probably the worst of the worst. And so when we send a notification that this incident has occurred, that's what we're going to send you. We're going to give you a little summary, and it's going to be that thing, okay? And we're hoping that when you look at it, you get the reaction like, oh my God, I got to take care of this. That's the intent of that. But what else is in this are things that probably led up to that thing that's really bad. And those are going to be anomalies that probably started here earlier in time. And maybe that's the hallmark there potentially in this diagram potentially. So these are things that led up to it. These are going to be pretty good candidates for looking around those as being a root cause, because they started the problem. That's what first happened, and then it got worse and snowballed and turned into this thing. So that's what we're trying to do in an incident: pull all of these things together in a concise manner with some real keys to sort of pinpoint you and direct you into the right thing with as absolutely as little effort as possible, all autonomously. You don't have to do anything for this to work. If you start ingesting us, you're going to get incidents probably within the day. And it might be because we're still in the learning process. I mean, it takes, can take a few hours for it to settle down and start learning those patterns. So we might, I would say we're always way better with not having any spam like that after the first few hours. And then it just settles in. And then when you get one, it's going to be probably meaningful. And then we have some feedback loops where you can sort of say, yeah, I know this, I know about this. Yeah, it was a real problem. I'm going to mute it because I know about it. I'm not going to fix it yet, but I don't want to see it again either. The other one's spam. Maybe we just got it wrong. You can tell us that. We won't show you those ones again if we ever see it happen again. And then for like, I mean, we love getting the likes because we know we're doing a good job, and we know what's meaningful to customers, and we can, you know, we look at every one of those to understand what's going on, no matter what selection they make here. This is kind of a manual feedback loop right now, where we really pay attention and look at these things to help improve the product. Okay, finally to metrics. But let me stop there real quick just to see if there's any questions again, or Salim, if you have any comments.
No, this looks good. Thank you.
Okay.
I just want to open it up to anybody else if they have any questions.
I do have a question around, this is a little Kuha. Can you hear me?
Mm-hmm. Yes.
Great. So in the correlation there, how do you ensure you're getting enough coverage on the different logs around the system, right? Not everything emits logs for you. So, you know, it's observability in that context. If you have enough coverage of your application, you're great. If you don't, then you're missing something, you know, there's a gap. So I'm curious how you handle that situation.
Good question.
Right. I mean, so we are obviously, you know, very dependent on logs. There is a few other things though that I'll talk about here. So obviously metrics are another one. So, you know, maybe we don't always have logs. We're going to talk about metrics. Metrics actually nowadays play a role in the creation of those incidents. So they are another anomalous kind of signal to us. And so that also feeds in. So if maybe we're not getting log events from something that's being monitored through metrics, then we might still pick that up based on those metrics. The other thing that that's somewhat applicable as well is we've just deployed and released a new feature where we can take external signals from literally anything. So here's a scenario. So let's say you have an APM tool. And again, this may or may not be directly applicable with what you're saying, but it may help the matter. So here's the scenario. So let's say you have an APM tool that's monitoring something, and it's that APM tool has, you know, some latency has gone through a threshold, so it fires some alert, and that alert you send to PagerDuty as an example. So we have an integration with PagerDuty that says when they create an incident for that reason, they will tell us as well. So the integration is to send us an external signal. So whatever that time is, we'll call it 10:02 in the morning. So what we will do is with the logs that we do have, even though maybe that signal came from something else where we're not getting logs, for the ones that we do have, because, you know, maybe there's a latency on something that's not sending logs, but there's other parts to these complex systems, obviously, that are going to be interplaying with that thing. So what we will do is we'll take that time, 10:02, and we'll immediately look backwards in time by a half an hour to see if there was any other kind of incident that we had already detected. And we'll update PagerDuty with a link and a comment in the Hallmark event to tell you, hey, you know, you're dealing with this problem, you should go look at this thing. And then as we're continuing to ingest data, we look forward for another half hour to see if there's anything else happening. I'll tell you about that. But even more importantly in this case, potentially, is that when we get that signal at 10:02, we will actually sort of sweep up anything else that didn't create that wasn't part of an incident already. We'll sweep it up and we'll make this synthetic incident so that you have all of that at your disposal. And that could include other metrics, could include logs from anywhere. We'll just sweep that all together and we'll build the right thing into an incident and put that into the PagerDuty case as well. You can do all of this from the Slack as well. So let's say it's 10:02, you don't have PagerDuty, but your APM tool fires. You can just say, Zebrium, help me analyze this, and hit the enter button, and we'll do the same thing for that. So that's a way where maybe, given that other signal, you know, from an external system, that we might be able to still help. I don't know, Larry, if you have any other thoughts on where we go with sort of the situation that was described here.
No, I mean, that makes sense. I mean, you know, I mean, you can only be as good as the data you get in, right? So
exactly.
right? So we encourage people to collect, as much telemetry as they can. And the more you get, the better the cross-correlation algorithm gets that determines incidents. I don't know if you want to get into that, Rod, or... Yeah.
Okay. No, I mean, let me carry on, and then we can, maybe at the end, I'm sure there'll be people that want to get into the even deeper stuff. So let me get through the metrics, because I know everybody's anxious to hear about metrics and also see a demo. So let me do this real quick. So we understand that, yeah, it's important to have metrics. We started with logs, again, for the reasons we said. It's the thing that can get you to root cause. So stuff that's hard. We started with the hard stuff first. We understand the importance of metrics, and when we thought it through and decided that we need to do metrics and sort of ingest those and correlate those in the same anomalous ways that we would for log events and E-types, we thought it was a very obvious choice to use Prometheus. I mean, it's prevalent out there. It's got a ton of exporters for all sorts of systems. It just made a lot of sense to not go and reinvent the wheel or think we're going to build our own collectors for logs or for metrics. We're going to use something off the shelf, and that was Prometheus. There was no doubt about that in our mind. So that's what we did. So we started with Prometheus, but we had some pretty stringent requirements, because when you're doing anomaly detection, there's a lot of things that matter with getting data fast. Like, you want to get it coincident with logs if you can. You don't want the metrics to come in 20 minutes after the logs and we've already got an incident going. We want these things to be as close in time as and as near real time as possible. So that's a requirement. It's kind of obvious. I guess the other thing I should mention in that one is when we're sending these logs or these metrics from somebody's environment, we want to try and make that as efficient as possible, because they might be getting egress charges and everything else. And just from an efficiency of bandwidth perspective, for those reasons, but also just from a transmitting as much data as fast as possible. Great to have a smaller bandwidth and compress these things or what have you. So that was important. And then the ability to type each metric. So we really, for proper anomaly detection, we need to know what that thing semantically is representing. Is it a counter or a gauge or a histogram? If we just got the number 2, we need to know a little bit more context about what that thing is, and so we have to preserve that. We have to get that information. So that's a second requirement. And then, from our perspective, the way we do things with getting things into the database, we can handle out of order stuff, and so we don't want to miss or not get something because something else decided it was out of order and therefore it wasn't going to fit properly into a time series database, so don't bother sending it. We want everything. We don't care about the ordering. We'll figure that out. And again, that's critical to anomaly detection for us. And then similarly for differences in timestamps. So, in Prometheus, these timestamps can get bundled together. Sometimes if they're different, they get omitted in inserting those samples into the database. We still want them. So that was another requirement. So while Prometheus obviously had tons of benefits, we also needed to meet these requirements. And then the next couple. So, you all know, if you're familiar with Prometheus, you're always getting time series for related kind of things. So like for CPU, I don't know what there are, there's a dozen or more sort of CPU related metrics that are like CPU user time, idle time, interrupt time, blah, blah, blah. So we want to be able to automatically group those together without any explicit direction from the end user. And so Prometheus was, because they do categorize these things in the manner with a sort of a well-known naming convention for them, that was very handy. And so that helped us, sort of get through this and be able to automatically group these through learning, what those patterns look like and being able to group them together and keep them together in that manner. So that was important. And then the last thing here is really, and one of the most important things is really to be able to correlate the metrics with the log events. And so when we deploy our Kubernetes collector, we're collecting all sorts of metadata, as you know, if you're a Kubernetes user at all. And all of that, from a log perspective, for every log event in our system, we have all of that metadata tied to every individual log event. We want that same stuff tied to metrics, so that we can correlate that these metrics are from this host or this container or this service or whatever it is, because that's relevant. Like, you don't really care about an anomaly occurring in some system that has nothing to do with the anomalous events that are making up an incident on a completely other system, completely different system that have no relation to one another. So you need to be able to tie this stuff together. So that was the sort of the sixth, big requirement that we had. So what we did was we looked at Prometheus. I mean, we were going with Prometheus for sure. I mean, that was a no-brainer. What we look at here is the remote storage adapter that is part of Prometheus. That basically, when the scraper runs and it's sort of going to store that metrics data into the local storage in the database there to be consumed by whatever, alerting or charting or what have you. It can also send it out to this remote storage adapter that will then write that data to some remote location. That is typically used for sort of replicating that local storage into a remote place in some manner, but and typically used for storing it long term. So if you want to store your time series data for let's say a year and a day or something, you probably put it into a remote storage. You're not going to keep it contained on your Prometheus server. So that's what that thing was really built for, and I think is primarily used for that. The problem with that is that some of the requirements that we had, you can't achieve by using that remote storage adapter. Like, for example, when you ship that stuff out of the adapter, you don't preserve what kind of metrics they were, like whether they were gauges or histograms or what have you. You kind of rely on the user to sort of see what it looks like. It's like, okay, that's a gauge, so I'll sort of do this with it. So they go by the name or by the help or whatever. But we need to know definitively. So when that's, taking that endpoint as being, sort of the solution for getting stuff to us, just for some of these reasons, we just could not meet those requirements. And it's not as concerned with bandwidth because it's going to be something that's, where that remote storage actually is still probably on-prem to where your Prometheus server is. It's just maybe a V for your database or something. So it's not optimized for, sort of for WAN, bandwidth. So what did we do? So we actually made some changes. So that storage adapter we ended up not using. So what did we change? So we removed some unneeded modules and we added some modules to support these additional requirements. So for example, the Prometheus server, we kept the scraper, we kept the service discovery and the config parser modules, and we removed all the other modules. So we don't even have the local storage component in there. So when we deploy, or when you deploy our Prometheus collector, let's say through Kubernetes, you're going to deploy it alongside one that you already have. If you already have one, you just deploy it alongside. It's very lightweight. It's running, like in its own container, and it's, doesn't require any storage or anything else. So we pared it down as much as possible, and you just deploy it with your existing one. We can use the same config. So there's no other work that you need to do there. Just deploy it and it's done. So we're scraping everything twice ultimately, but it's not a big deal. So we did add 3 new modules, and they're called the Z-Packer, the Cacher, and the Queue Manager. And basically these are the kind of secret sauce behind how we achieve those other requirements. And so I'm going to walk through them real quick. I think we want to get onto the demo, but I do want to cover this because all of this stuff is out on Git for anyone to look at or use. But I'll just go through it real quick at a high level. So the Z-Packer. So basically the way to think of this, when we scrape something, so we're using the existing scraper, so we get this set of metrics, for one set of time series so one metric from each one metric of each thing that is scraped. We call that a blob. Okay. So the Z-Packer takes that thing and it sort of blobs it, makes this blob out of it. Okay. It makes 2 blobs. It makes a full blob and what we call an incremental blob. So the first time through, you can't make the incremental, there's only got one. So that full blob is put in the cacher and it's sent home. Okay. So it flushes it over to the, something will store it up and then essentially move it over to the queue manager. Queue manager is responsible ultimately for getting the right blob back to our backend, whether it's a full blob or an incremental blob. So the next thing that happens is scrapes again. Now you have the opportunity to do incremental because you've got one complete. Now you look at doing incremental. But you take that thing that you scrape, you create another full blob and store that in the cacher. But you take the previous one and you diff it in various ways. So we diff timestamps, and we diff the data changes of the actual metric itself. And in a lot of cases, the things didn't change. So you can sort of encode those right out of the payload. And if things really haven't changed even to the level of labels, which they probably don't change frequently, so the actual labels that we're collecting as part of our collector that that we match up with the Kubernetes key value pairs, if those aren't changing, we discard those because they've already got the full blob and say, hey, here's an incremental, the one you got. So if they need anything further that we don't send them in the incremental, they already got it anyway at our backend. So through these various techniques that the Z-Packer is using to sort of condense that blob and send these incrementals, we're extremely efficient on what happens. Now, let's say something does change. Like, let's say something big changes, like new exporters are brought online. So it's up to the Z-Packer to recognize that, and they'll say, okay, can't do incremental anymore. They need to get all of this, baby, because there's all new stuff in it. So that'll create a full blob. It'll create, and then it'll send the full blob down. So every once in a while, we might have to send a full blob, but the next one is going to probably be incremental. So that's what's going on between these three modules: the caching, the packer, and then the queue manager, which is taking those blobs, whether they're incremental or full. It actually is coalescing them. It's not just sending one every time it gets one. It's doing some work to coalesce things. And again, for efficiency, because the overhead of making that post call back home, if you can pack several blobs into it, you get less overhead on the actual post, as opposed to doing it 10 times or something. So it does that sort of work. If at the other end, the ZStats server on our end can't reconstruct what it needs to for whatever reason, maybe something crashed somewhere, it'll ask the queue managers, hey, send me back a full blob from blob. That way it'll go back to the cacher, it'll get the full blob, it'll send it, this guy will be back in sync. Okay. So that's kind of the process that we're using to make these things efficient. And we get somewhere, like if you were to take, well, let me finish this other thing first. So what the ZStats guy on this guy is doing here at our backend, he is ultimately taking all of those incrementals and reconstructing the full Prometheus file that would have gotten ingested into a local database on the Prometheus server. So it rebuilds everything up to be exactly as it would have been had it been scraped and stored locally. But we preserve all these things that we needed to, that I outlined in those various requirements. So that's what that's doing. So ultimately that packing and compression and encoding and sort of deduping that we do in the packer, that equates to about a 500x reduction in data that has to go across the wire from what it would have looked like going to the local storage as a sort of this Prometheus file format to what goes across the wire to our endpoint. It's about a 500 to 1, call it compression. So this again is all sort of detailed. If you guys are interested, or if you want to go look at it further or see, there's actually an outstanding blog that the engineer wrote that did all the coding for this thing. That really goes into a lot more detail than I have, and it's actually a really kind of interesting read. I should point out that we forked this, so it's not into the main project. That is something on our roadmap to sort of take that remote adapter. I mean, what we're thinking, you take the remote adapter and you take our kind of gears that sort of does the packing and everything, and you put some shim in between the base line that would allow us to either be plugged in or the remote adapter to be plugged in. So it'd be easy to interchange whatever output method you want to use, either the one that exists or ours. And then of course we also provide the code for the remote server, like what does it have to do to sort of reconstruct the full payloads and Prometheus files. So that's part of what the remote server does. All right, so as you would expect, we still do everything we do today with logs and everything I described there. We do very similar, we do anomaly detection on metrics. So if we see spikes happening or things drop, there's a few features like that we detect in metrics. And if they're occurring coincident in the same manner as log events are, as anomalies in a time frame of an incident, then they will get included as part of the input to that correlation analysis. and ultimately end up in the incident, and that's what you see here. And so when you're in our UI, you can actually click on this and you can drill down, and you have all the Prometheus metrics that you're collecting are all at your disposal within our UI. But this one in particular will, you know, when you click on this, you'll drill down to that exact metric that's relevant to this incident. And with that, I guess the summary here is that, you know, all of this is for the pure intent of trying to trace the unknown unknowns and getting these incidents to you in a fast manner, a manner that's relevant and that's going to get you to root cause quickly without any special connectors, knowledge bases, you know, having to understand any specific application behaviors or semantics of the events or anything else. We just work great on bespoke apps or any stack, and that's our objective, and that's what we do. And I guess now I will any questions first, and then after that, we'll hand it over to Gavin, who's going to do a demo and just show you the stuff in action.
Well, I have a bunch of questions. I want to see the demo first.
Okay, I got to stop sharing, Gavin. Hope you're still awake.
I am awake. I am just on mute. So just confirming everyone can hear me and see my screen. Is that a yes?
Yeah, we can see your screen.
Okay, terrific. So look, I know we've probably gone a little bit long, so let me just get straight into this. So this is an instance of Zebrium, or an account on the Zebrium service that's actually monitoring the logs and the metrics coming from our production Kubernetes Atlassian instance. So we run the Atlassian apps, Jira, Bitbucket, and Confluence, and this is actually our production instance. And last week we injected 2 problems just to see, you know, make sure we're all still working really well. And it's pretty cool because you'll see in a moment that's exactly what we detected. So this is an overview screen. You can see CPU and memory utilization that we're pulling in from metrics. You can see over time a chart of errors and anomalies. So just important to point out, there are always anomalies. These are the noisy things. You always have events out of pattern or metrics that are outliers. That doesn't mean there's a problem. The key thing is what Rod was talking about, which are these correlations of, you know, hotspots of abnormally correlated anomalies or virtual traces that we build that actually represent incidents. So underneath it all, our machine learning has pulled out 2 incidents. Okay, so I'm going to click on that, and you're taken to the incidents page where we list a sort of a 1-line summary of each event, each incident. Okay, I'm going to start with the bottom one, which doesn't have metrics, and then I'm going to show you the second one, which does. So this one's actually pretty cool, and I'll do it quickly, but essentially this is what the incident looks like. So you can see here in this color, I never know how to describe that, if it's purple or red, but this color is basically that hallmark event where we think is a really important event for you to see if you see a 1-line summary. And this incident actually spans Bitbucket and Jira, okay, and the Postgres exporter, as well as their events from syslog. So this is clearly an ominous event, and it's fatal severity. So everyone would say that's not a great thing. But what's really cool is if you go up to the top, the very first line in the incident is actually an info level message from syslog, essentially saying Postgres stopped. So to cut a long story short, someone logged in, they shut Postgres down, and what ended up happening was soon after you can see some SQL exceptions coming from Jira because it's trying to talk to Postgres that was shut down. So you see this cascading effect. And then you see, you know, again, I won't go through each event, but over here, Bitbucket's impacted where there's, again, a SQL exception where it, you know, terminates, and you can see some failed queries over here and so on. So pretty clear cut, Postgres stopped. And important to point out, there was no rule here or alert rule set up or anomaly detection rule for these types of events or anything like that. This was 100% machine learning, our machine learning, finding those correlated anomalous patterns that spans that it thought were rose to the level of raising an incident. This is exactly what happened. We shut down Postgres, all the area pressed for time, but I can stay on and show you a whole lot more. We can drill down to see what else was going on. And that's pretty cool too, because here we're like a full-blown log manager. So what you're taken into initially is a filtered view of those same events. So you can see spanning syslog, Jira, Postgres exporter, Bitbucket, and how it cascades. These look much more like the raw event format that you would have seen if you were looking at those log files or streams. And we can, over here, we can do a few cool things. We can peek to see what else was going on. So now we're taken into syslog. We're left in the same spot as we were before, the stopped Postgres message, but now we can scroll up and down and see what else was going on in syslog if we wanted to explore that way. We can also, I'm coming back to my filtered view. We can turn off the filters that were coming in, starting with this one. So you're seeing it updating now. Here's our stop Postgres. And what's pretty cool is if you look a couple of lines above, very quickly you can see Rod, the person who was just talking, had opened a root session, and you can see this command was executed by root to stop Postgres. So it was a nice clean shutdown, not an error, and then everything fell over. And I'll show you an event. You can see there are some words in white and some words in blue. The one's in blue for this event type, but we know that there is some fixed text called PostgreSQL cluster, and there's some variables, including the word stopping. So let's take a look. Let's do a chart of the word stopping. And you can see over time, we can show you that there were values of stopping, stopped, starting, and started. And that's actually what happened. 2 minutes later, you can see that at the timestamp at the top, Rod actually started Postgres, and you get the Postgres starting message, and then all the other apps start to the things you can do because of the machine learning. But let's go back to our incidents view. And remember, I said there's a second one. So this time, this is the new work that you saw Rod talking about with Prometheus scraper that we did and Prometheus server. And what we're seeing now is an incident that includes both logs and metrics. So here we've seen some but I can click and I can drill down and zoom in and look at other correlations and so on. So that lets us do some cool things. And we also have Grafana support if you want to do some cool things with metrics or even some of the log data that we've passed out. But again, let's start. Here's our hallmark event. So what happened here? This is again on our Atlassian instance. And you see here there's some kind of Java exception trying to create a session. And what was actually happening at the time is the whole system had ground to a halt. So you couldn't sort of do anything, you couldn't log in, you couldn't update the screen, whatever. So at first appearance, you'd say, okay, there's some sort of a Java issue. Then we look at metrics, and you can see here there's a JVM memory pool, bytes used that fell out of range. Actually, it looks like even twice that happened. It suddenly dropped. So that would sort of be in line with some kind of a Java issue. But that's not the root cause. If we keep looking up and you go a few more lines up, you will see this interesting event. And this is a kernel event. So again, we didn't instrument for this or look for this, but this one's essentially saying that the kernel invoked the out-of-memory killer process to kill a rogue process called OOM test. And that is actually the root cause. So it turned out that our user Rod was running a program called OOM test, and its whole sole purpose in life is to allocate as much memory as it possibly can. And what it actually did was it starved the JVM from getting memory. which caused it to fall over and have all these exceptions and caused all the apps to sort of freeze up, which you'll see if you look, because this app, if we look at all the events, you can see it actually spans Confluence, Bitbucket, Jira, where there are all kinds of issues going on. This was the root cause. So it beautifully picked that. It actually picked the rogue process that had nothing to do with the Atlassian stack at all, because it found these sort of out of sequence patterns that correlated with everything else going wrong. So let me stop there, because I know we've sort of fallen out of time, but I'm happy if people have questions, we can dig deeper. We've got Rod and Larry who know more about this than I do, who can also answer any questions. Someone has to be the first to ask a question.
Yeah, I actually have a question.
Point out, just if anybody's interested, just really quickly, I was going to say there's, you can sign up for free and start using our service. Just visit Zebrium.com and you'll see it's pretty obvious, the sign up link. It takes about 2 minutes to install Log Collector and start to get this kind of a view. And it's pretty cool what you'll see. So sorry, I'll stop there. Salim, did you want to ask something?
Yeah, like if we're already using another product, do we have to like uninstall it and then install Zebrium, or how does that work?
I might start with that.
No, you would just, you don't have to do that. So if you can just deploy our charts and it should be independent. You mean like if you're using like some other metrics collection or analysis tool, or if you're,
like Sumo or Datadog or Elastic, because I know some of our clients are already using that. So
yeah, that's no problem. I know we're installed in a number where
there's actually
okay.
There's actually a very cool use case there that Rod alluded to earlier. We can actually, so let's say your primes and it's working beautifully and it detects the things that you want to detect and symptoms that you care about. We can actually take a signal from a tool like Datadog if you use PagerDuty to help feed the signal to us. And that basically informs our ML that an incident has happened, and we'll respond to this sort of incident type of summary that you see here that will help to inform what actually happened. So this new use case is really, we augment someone else's detection. So if you have detection in place, we can actually feed it the root cause, and it can be done either using something like PagerDuty, where we've automated this whole process. So the Datadog alert would come in, and then immediately you see the incident using that to manage your incidents. You can type in a command to tell Zebrium basically come back with an incident and a synthetic incident that builds around the signal that it gets from something else.
Oh, interesting. Okay. Go ahead.
Yeah, I have a basic question. So how the Zebrium differs from the other SIEM tools like Splunk or Exabeam? They also kind of act as log monitoring and machine learning based anomaly detection systems, right? So how this solution is different from the other tools?
So what
Larry, do you want to take that?
Yeah, so right. So most of those tools, will give you a place to put your logs, search them and chart them, and your metrics, and some of them give you some level of anomaly detection. But we do something completely different on top of that, which we kind of went over it during the slide deck. But essentially, instead of trying to have you sift through anomalies and various data, what we'll do is we'll detect when there's an incident, and then we'll send you basically a virtual trace of that incident, including the logs and metrics that you need to root cause it. So it's a completely different way of approaching data. So instead of you telling the stack what to look for, it tells you what to look at. That's the purpose of it, and it does a pretty good job. So if you're skeptical, I would be too, and the best thing to do is to try it, because it works pretty well.
Sure. Yep. Thanks.
Thank you.
I have two questions. guys. One was, if I've already got Prometheus installed, I'm looking at everything, I have to create another, how would you feed it in? Because I already have the explorers, I have the C advisor, node exporter, everything else.
So that's
Can you
all
take
good.
advantage of that?
That's all good. That's all really good. So there's really three parts to it, right? There's the exporters. There's the sort of main Prometheus application with the database, and then there's the scraper, right? And so the scrapers, we deploy a custom scraper. It's on our GitHub. It's very lightweight and it streams data over the network. But it can scrape the exporters you have, and you don't need to install another Prometheus server either. It's kind of how that would work.
So you just deploy us, like you would deploy our log collectors, but you're deploying a Prometheus scraper. So it's a whole new instance separate from yours, but it's scraping the same endpoints that you have already defined as exporters. So you don't have to do anything else other than just deploy it, and it'll just start doing the right thing.
Is it being deployed as a daemon set, or what is your scrapers?
Yeah.
Okay.
Well, but there's going to be one instance per cluster as opposed to the log collectors, which will be one per host.
Sure, makes sense. And the next question I had, or maybe I should let others go.
No, go ahead, Alok.
Under what situations, because you're correlating, that's an interesting idea, right? You got the logs, you see the events, and you're trying to figure out there's metrics that might be relevant based on what you're doing. But the way you've captured all the metrics, those names may not be the same as the names of the containers or Kubernetes services. How do you associate those? Do you see what I'm saying? There's a name mapping required, or that's how you did it from your free parsing versus what Prometheus natively does.
Right. So setting the names of the metrics aside, I think you're talking about kind of the labels that might end up having container IDs or whatever, and how are we knowing what container it came from, the metrics that are being scraped? Is that the question? Because what we do in our scrapers, we actually keep track of what hosts and what containers on those hosts are being scraped and which scrapes belong to those, in such a way that we're doing the same kind of mapping in our log collector. So when we get it back, we can join them.
So Larry, the other thing hi, this is Anil from Zebrium too. So the other thing that we do is that our custom Prometheus scraper would add these extra labels so that we can join with the logs for those container. And then the other thing important thing that we do is, for example, let's say you have Prometheus has multiple metrics for CPU, like idle, busy, and a lot of other things. So our backend, we would be able to group all those similar metrics and then do anomaly detection on a group level instead of doing it one metric level. Does it make sense?
Yeah, I think, thanks, Anil. What I think I understood from what you just said, the prior to your group comment is, you may have to add some extensions to the labels that come naturally from the Kubernetes space to be able to make them, kind of map them to the names you've created for entities related to those containers.
Yeah, that's right. So our scraper does that. I mean, our Prometheus scraper that scrapes your exporters would add those labels automatically so that we will be able to do the joining.
So you don't have to manually enter them?
That's right. You don't need to manually enter them.
Would make sense. Okay, cool.
Okay, and I have one question. What does it cost?
Well,
That's cheap.
Let me try. Someone mentioned that there's poor sound, so someone can translate if I don't come across clearly. Essentially, so we have a free plan, and that's free perpetually for up to 500 megs of logs a day and a couple of metrics hosts. So anyone can use that perpetually. And then we essentially charge based on log volume and then there's a small charge per metric host. So it's fairly nominal, and it's, if you compare, someone mentioned Splunk before, it's probably a fraction of what you would pay for the equivalent of Splunk. You can see all the pricing on our website. That's pretty obvious.
Yeah, we try to be really transparent about the pricing.
Yeah. And what do your like small, medium, large customers typically pay? Like what?
You know, I mean, we have plenty that use the free service and love it and love us for it. So that's great. It can range from as small as sort of I think the minimum billing is like $45 a month that we bill. And we have customers that could be sending terabytes that are obviously significantly more than that. But you'll see the pricing. It's pretty cost effective. And we also have, if you use that augment workflow that I talked about earlier, there's a special plan for that, which is about half the price of the normal. And that's because we don't retain things for very long to be able to augment. So, but it's all there. It's pretty clear on the website. There's a pricing page.
And the 500 megs, is that based on the compressed, like the 500 to 1 compression that you guys were talking about, or is it based on the regular log size?
So that's actually the log volume, and that's the raw log volume. So 500 megs of logs a day, and then the metrics, I think they're 3 metric hosts we support for free.
Okay. All right.
Do you guys support on-prem or only the cloud-hosted solution?
Oh, that's a good question.
So we have so the answer is, for very big deployments, we can. It's not our normal mode of operation, but we do have, in the cloud offerings, we actually offer a private VPC where you get it's not a multi-tenant instance, and it can even be one that you own. So we can actually deploy, if you use AWS, we can deploy in your VPC, you own it.
Got it. A dedicated environment for us where we push our logs from on-prem to that instance.
Yeah.
Right. Exactly.
Got it.
I mean, yeah, exactly.
Okay. Thank you.
No problem.
This was great. So thank you. Does anybody else have any other questions?
I think, as I said, this is great, and we'll try and provide the feedback. I think.
Yeah, it'd be awesome. Appreciate that.
I mean, we love feedback. We're a small company. Any feedback you can give us is fantastic. We absolutely love it.
Yeah, we turn stuff around quick too, kind of at that stage. So.
Well, congrats on getting on the AI 50 list.
Oh, thanks.
Yeah.
Yeah, thanks, Salim.
Yeah. All right. Well, thank you everyone for coming over, and if there's any other questions, how do they reach you, or how do folks reach you guys at Zebrium?
So we can post our direct contact details on the Meetup channel. If you visit zebrium.com, basically it's hello@zebrium.com. We'll get through
perfect.
to the sort of the core team, and we'll respond.
Okay. All right. That sounds good. Okay. So I want to thank everyone on the call, and then we'll call it an evening then. So.
Okay.
All right.
Thanks, guys. Appreciate it.
Thanks, everyone. Take care.
Thank you.
Bye.
Bye.
Bye-bye.
Thanks.